Hi, good morning. Can you hear me in the back? Yes? Okay. Now? So first of all, I wanted to thank you, Mikhail, for inviting me and Eurostat to come to give this presentation. I don't think I've ever given a presentation in front of so many statisticians. It's kind of intimidating, so please be kind with me. Mikhail said, I'm just going to give you in about 40 minutes a high-level description of 3 exemplary projects that we have carried out that I think are in the intersection between official statistics and computer science, or where I see the role of big mobile data in the context of official statistics. So before I do that, I'll just very quickly give an introduction to Telefonica Research, because it's a new organization that we created. I helped co-create, in my case, 7 years ago, so you might not be familiar with it. We are in this building that you see on your right, on your left, sorry, in Barcelona. It's a small organization. In total, we're about 20 full-time researchers, but we do have an internship program for PhD students to come and do work with us for 3 to 6 months on research projects. And we also have the option of visiting researchers or professors to spend some time also working with us. So we follow an open innovation approach. We collaborate with many institutions, both mainly public institutions or universities, and in fact one of the projects that I will present later was a collaboration with FBK and MIT. In the case of my team, this is my team. It's about 10 full-time researchers, and we work on a variety of topics, always with the goal of human behavior modeling and understanding from data. But the data could be not only mobile data, but also it could be audio or images or video, and the behaviors could be both individual behaviors or aggregate large-scale behaviors. In terms of the sort of like a high-level summary of the achievements of the group so far, I'm really proud that we, having been created this team from scratch, we've gotten a lot of external visibility so far. We've filed many patents, we've written many papers, and we've gotten a number of awards, all, you know, when the team didn't exist a few years ago. So for me, that's really, you know, it brings me a lot of like pride and excitement. And our work has also been featured recently a lot in the media, and I think this is a reflection of the importance of big data today and the realization that big data has the potential to have real positive impact in the world. And we've been working on these topics for the past 6 years, and it's only been in the past 18 months that we've seen so much interest and activity outside of the scientific community. So this is something I think very indicative. Even the fact that I'm speaking here, you know, in this room is something that, you know, maybe it wouldn't have happened 6 years ago. In terms of my personal trajectory, as Michalis explained, I started my research work at the Media Lab at MIT, and my goal has always been modeling human behavior. And I started doing that using cameras and other sensors and microphones. I did projects for recognizing facial expressions, recognizing interactions between people, and because I happened to be in the same group that created, or that was one of the leading groups in the world in wearable computers, I also interacted and worked a little bit on wearable computers. And in fact, the researchers from that group were involved in the creation of Google Glass, you know, almost 20 years later. And I also had the opportunity to build a smart car, where the idea was to build a car that would be able to predict the most likely maneuver. Again, this is human behavior modeling, in this case very multimodal, because I was using loads of sensors in the car. And then in 2003, when I was at Microsoft Research in Redmond, I had an epiphany. And I realized that if I wanted to build intelligent computers that understood humans and that could model human behavior, the ultimate personal computer was the mobile phone. So I made a decision, which was to work mainly only with mobile phone related data, or with mobile phones, because I really believe that that's the most personal computer that we have. So I did some early work on, you know, what is called today wearables and gamification, but at the time there weren't any wearables available, so I had to build my own hardware to get the phone, monitor physiological signals, and recognize different aspects of human behavior. And then when I moved to Telefonica 7 years ago, we started doing a lot of work using the mobile data that is available to Telefonica being a network operator, and trying to model behavior both at the individual level and also at the aggregate level. And the work that I'm going to present today falls in the category on the right. So I will present 3 examples of projects of modeling human behavior from larger scale mobile data. So that's the brief introduction, and now I'm just going to go into the core of the talk. So when I was preparing this talk, and not being an official statistician, my first question was, what is official statistics, you know? I looked for some kind of official definition, and you all know this, but this was very helpful to me because we have done a lot of projects related to official statistics, but I hadn't properly looked into the definition. So the interesting aspect is the fact that, you know, the official statistics provide quantitative and qualitative information about different aspects of people's lives, including, you know, economic situation, social situation, you know, living conditions, etc. So it really has a lot of elements of human behavior modeling and human modeling, which is what I have been doing. If we look at, in more detail at variables that are important in official statistics, so we have population, we have gender, employment, economic situation, trade, environmental and energy consumption. And a lot of these variables, indeed, we can infer from mobile data. So I think there is a fair amount of intersection or possibilities of using mobile data for official statistics. When we look at mobile phones, and you probably know all this already, so there are as many mobile phones as people in the world, more or less. This data is actually a year old, so, or a year and a half old. The penetration worldwide is very high, according to the ITU, ranging from 89% to 120%. We love our mobile phones. As I said, I realized that it was the most personal computer. We spend more time on the mobile phone than on any other thing or with any other human being. So that's something for us to reflect on. And what is really powerful for, I think, in the context of official statistics is that this is a global phenomenon that is happening both in developing countries and in developed economies. And for me, that's the biggest power, because there are many developing countries where there is very coarse or very limited official statistics information, but most of these people do have a mobile phone. So I think that's where, you know, we could have a lot of impact. And in fact, many of the projects that we are doing are in the context of developing countries, because that's where we think we can help the most. In fact, we are not the only ones working on this. This is a new trend within mainly computer science. And in 2013, MIT Technology Review named this area of research of human behavior modeling from cheap phones or from any phone an emerging breakthrough technology because of the huge impact that it could have. In parallel, as you probably might be aware of, in United Nations, there has been a lot of activity in defining the new goals for humanity. And one of the actions that has been really highlighted is the role of big data in reaching the goals and the necessity for having a big data revolution of how we can really leverage big data to make the world a better place. So with all of this, the question that I'm going to try to answer in the talk today is, can mobile phone data be of any use for official statistics? And before I explain the projects, I'm just going to give you a 2-minute quick primer on what kind of mobile phone data I'm talking about. Are you familiar with mobile phone data? Have you analyzed mobile phone data in the past, any of you? Okay, so then this might be useful to you. So this is how a mobile phone sees the world. So the mobile network consists of a number of cell towers, and you might have seen some of them in the cities. And the cell towers give coverage to a certain area. This is a simplification of reality, but typically what you do is you do a Voronoi tessellation of the geographic space in such a way that in the middle of each of these cells there is a cell tower. And you assume, even though it's an approximation, that any phone that is connected to that cell tower can be within any position of that cell. So there is a certain amount of geographic uncertainty. The size of the cells, these cells here can be, they depend on the density of the cell towers, which typically is high density in urban areas and low density in rural areas. It can go from, say, 100 by 100 meter cell to a few kilometers by a few kilometers cell. The data that is typically analyzed for human behavior modeling from mobile phones is what is called CDRs, which means call detail records. This is an example of a short entry of a CDR. So CDRs are event-based data, which means there isn't a regular sampling rate for the generation of this data. It only appears when an event happens. And that event is the phone making or receiving a phone call, the phone receiving or sending an SMS, or there is another data set for the phone making data connections. So in the traditional making phone calls and sending and receiving SMSs, what you have is the encrypted originating number, the encrypted destination number, the duration of the phone call, and then the ID of the cell tower that the phone was connected to. Typically, you can map from the ID the location of the cell tower, and within the size of the cell, which could be, as I said, from a few 100 meters to 100 by 100 meters to a few kilometers by a few kilometers, you have a rough estimation of the location. From these CDRs, typically, we compute 3 types of variables. We compute consumption variables, we compute social network variables, and we compute mobility variables. Consumption variables are related to how many phone calls you make, and you can compute all sorts of possible variables: incoming phone calls, outgoing phone calls, duration of the phone calls, statistics about the phone calls, SMSs, etc. In terms of social variables, what you can build is the call graph, which is like a social graph of all the different people, obviously anonymized, that you have called or that have called you, or that you have sent an SMS or they have sent an SMS to you. And then you can compute characteristics of that call graph, the in degree, the out degree, which ones are the top, correspondence, the level of the reciprocity in the communication, etc. And then finally, because you have the ID of the cell tower that the phone was connected to, you can have a rough estimation of mobility. And some typical variables that are computed in terms of mobility is what is called the radius of gyration, for example, which is the radius of the smallest circumference that would comprise all the cell towers that a person usually is moving around. Or you can compute where is the distance traveled, the maximum distance traveled, or what are the top cell towers that the person is moving around, etc. Just to give you a flavor of how the data looks like, I'm just going to show you 2 short videos. The first video shows the activity in the cell towers in the state of Oaxaca in Mexico right before, during, and after an earthquake took place. So these bubbles that you see here are different cell towers, and the bigger the circle, the higher the number of phone calls that cell tower is serving. So this visualization only shows the activity levels at the cell tower. But only looking at that, we are finding that it's extremely powerful. So you will see there is an earthquake here now, and you'll see the huge surge on activity, and then after the earthquake, there's silence. So you could imagine being able to use the activity in the cell towers as a proxy of the amount of people that are around each of these cell towers, which is important in the case of a natural disaster. The next video shows the mobility of about 1 million mobile phones in the UK. And then, just by looking at the mobility panels, you can see the main cities, you can see the, the main highways, even like people going to Northern Ireland, etc. So again, this is very coarse data, but still, it has a lot of value when, in many cases, the alternative is no data at all. So in the context of the work that we have been doing that I think is relevant for official statistics, we've done work on understanding the impact of government interventions in the case of a pandemic. We've done inference of socioeconomic status from CDRs. We've done crime prediction, and also quantifying and detecting which regions are affected by floodings when floodings happen in Mexico. Today, I will just present the, and actually we've also done gender identification from data. So I'll present the gender project, the socioeconomic status project, and the crime prediction project. This is just some of the, looking at the variables that I mentioned before related to official statistics. These are some of the variables that I think, or where I think that mobile data can really help, compute them or have more accurate versions of them, because obviously one of the advantages is that you have the mobile data much more frequently than, say, the census data, which is computed maybe every 5 years. So I'll present first gender. This is a joint work with Vanessa Frias and Enrique Frias from my team. And that was one of the first projects that we did in looking at CDRs. So the problem that we wanted to solve, or the question that we wanted to answer was, is it possible to identify gender from looking at the patterns of behavior of using the mobile phone? Or are there any statistically significant differences in the way people use the phone depending on whether you are female or male? So to do that, we analyzed 2 million calls from approximately 5,000 females and 5,000 males, and we had 3 months of CDR data. I'll show later a slide with the main publications so you can read more detail about any of these projects. As I mentioned before, and as we do in most of the projects, from the CDR information, we computed the 3 types of variables that I mentioned: consumption variables, social variables, and mobility variables. Typically, you end up with a range from a few hundred variables to a few thousand variables, depending on how crazy you can go about computing statistics and more statistics about these variables. Also, because this is a spatiotemporal data, another element to take into account is the temporal aggregation. So you can do the temporal aggregation at a daily level, at a weekly level, at a working day versus weekend day, at a monthly level. You can split the day into different parts of the day and then do it mornings versus midday versus evenings versus nights. So you end up with a lot of variables because you try to split the data and represent the data in as many ways as possible. Something that you usually do just to start understanding the data is figure out or fit a distribution to the data. So this is, I'm not going to go into detail, but we just looked into which distributions fit it the best. Usually for this kind of data, the 3 main distributions that are always the best fit is either a power law or a log normal or an exponential. And I'm not going to go into the details in the interest of time, but I'll just share with you some of the insights. So in looking at the 3 types of variables, consumption variables, social variables, and mobility variables, what we found was that in terms of behavior, females did have significantly higher values in the behavioral values, significantly higher usage compared to males. And that was surprising to us because this was a developing economy, which we didn't know what was going to happen. In terms of social variables, we also found a statistically significant higher values of these variables for females versus males, but we did not find any significant differences in mobility between males and females. We also built classifiers to see if we could accurately determine gender, and one of the learning lessons there was, and this is very important to take into account, as I mentioned, this data is event-based, which means that you don't have the same amount of data for everybody. You have, depending on the level of activity of the people, you have people that are very active and you have people that are very little active. So what we found for gender identification is that only for the people that there was a significant level of usage of the phone, we were able to accurately discriminate gender. But most of the people actually in developing economies have relatively limited usage of the phone. And for those, there was such little data that we were not able to make any good classification. I'll move to the next project, which is socioeconomic status inference from data. And this is actually work by Vanessa and Enrique from my team. So I'm pretty sure you know about census maps better than me. The main motivation for us for this project was because socioeconomic levels, particularly in a developing economy, is usually a proxy to access to education or access to healthcare or access to sanitation. And we were interested in seeing, and of course there is a scarcity of this data and this information in developing economies, so we were interested in seeing the value of mobile phones in this case. So usually socioeconomic levels are computed from a lot of different variables related to census, and it's at the bottom, I don't know if you see it there, the socioeconomic levels. And typically they range from A to E, at least in the countries that we were looking at. So one of the challenges is that computing socioeconomic levels is very expensive, and usually this is done every 5 to 10 years because it's extremely labor intensive and very expensive. So the question that we wanted to address is, if we can compute all these different kinds of variables from the mobile data, could we build models of socioeconomic levels so we could actually infer the socioeconomic level directly from how the phone is being used in these different regions. So these different regions are usually the geographic regions that characterize a specific socioeconomic level, and they're sort of like at the level of like a zip code. We knew that there was previous work that had showed that higher socioeconomic status is correlated with larger mobility, and also lower socioeconomic status is correlated with a smaller size of the social network. So there was some previous work indicating that there were correlations between the socioeconomic level and mobility variables and social variables. So that was a good starting point to address this problem. So that was the question that we wanted to answer, and this is how we did it. So most of the approaches that we follow are supervised within the supervised machine learning approaches, which means that you train the models with some data and then you test them on unseen data. So in the case of this project, the idea would be that you have the ground truth for part of the region of a study that you want to characterize, and then you analyze the aggregated mobile data for the entire region, you build the models, and then you can infer the socioeconomic levels for all the regions that you didn't survey and you didn't do the official statistics in. So just as a recap, we used the same data that I explained before, CDRs, and in this case, it was for one city in Latin America. There were 1,200 geographic regions, the little regions of description of the socioeconomic levels, with 3 levels. And we split the data into 2/3 for training and 1/3 for testing. And we created hundreds of variables. And then we used different techniques for feature selection. Usually in most projects, you go from a high dimensional space to a lower dimensional space, applying different feature selection techniques, and then you build your models from that lower dimensional space. We tried different classification algorithms, and I'll just report the results using random forests, which I'm not sure if you're familiar about, is a well-known classifier. Something to mention, there are many approximations that you make in this process. And one of the approximations that we made was in the context of the geographic regions. So the geographic regions of the socioeconomic levels, which are this pointer, I'm not sure if it works. I don't know what it is. Well, on the left, and then you have the actual coverage cells of the cell towers in the middle, and you have to make them somehow overlap. So we just applied sort of like a linear approximation, so we could represent the cell tower coverage as a weighted sum of the different socioeconomic levels of the different regions. So applying the random forests, we were able to achieve an 82% accuracy in determining the socioeconomic level. And I'll just leave it there. Something very interesting for me, actually, maybe one of the most valuable aspects of doing all these projects is looking into which features are the most important or are the most discriminative for that particular problem. So in the case of socioeconomic level inference, we look at the top selected features by the classifier, and it's interesting because there are features of the 3 types of variables. So we had mobility was very important, and many of the features were related to mobility, but we also had features related to social variables and also consumption variables. I'll just skip this in the interest of time, and I'll go to the last project. So the last project was a collaboration with FBK and MIT, and it was a project to infer crime hotspots in different geographic regions. So crime is important because it affects the quality of life of a region, and it affects also the economic development of that region. There are a number of studies that have been trying to find correlations between crime levels and different statistics, official statistics information, or socioeconomic variables, education levels, levels of like immigration, unemployment, etc. And the latest methodology or the latest approach in crime characterization is the creation of what is called crime hotspots, which are small geographic areas where crime seems to happen a lot or seems to accumulate. So we will also, in this project, try to find these crime hotspots. In terms of the theories for crime, there were actually two competing theories. One, and I don't know if you're familiar with crime. So there was one theory by Jane Jacobs, which was a social activist in the 60s in the US, and she talked about the concept of eyes on the street, where she said that if you have a region or a city that has a lot of diversity, that has a lot of people going in and out, we all act as policemen of each other, and that would be safer, because we are all looking out for each other. But then a few years later, there was the opposing theory by Newman, where he was saying that if you have a high mix of people, you are having more anonymity in that space, and that leads to more crime. So one of the questions that we wanted to answer with this project was, who is right? What is the reality? Is it crime correlated with diversity, or is it inversely correlated, with diversity and amount of people? Another very important element in crime models is people-centric models versus place-centric models. So when you think about crime, many people think about a minority report, like predicting whether an individual is going to commit a crime or not. And in reality, most of the models today are actually place-centric models, which is related with I mentioned about hotspots. So our model is not a people-centric model. There is no individual analysis, and we're not trying to determine whether any individual is going to commit a crime. What we're just trying to determine is how safe a particular neighborhood is, and where these hotspots are going to be happening in space. So I just explained that. We followed a multi-model approach, so we not only use mobile data for this project, we use additional data, which I'll explain later. As a use case, we used the metropolitan city of London, the metropolitan area of London. And this project was done in the context of a datathon that Telefonica organized, which was carried out together with the campus party in London in September of 2013, and it was called a datathon for social good. And actually, this project was the winning project for this datathon, and then later on, I became involved and I started the collaboration with them, with FBK and MIT. So there were 3 data sets that were shared. There were other data sets as well, but 3 particular data sets that were used in this project that were shared in the datathon. The first one was called the SmartSets data set, then there was the criminal cases data set, and then there was the London Borough Profiles data set, which is census information about the different neighborhoods in London. So the SmartSets data set could actually be quite interesting, I think, for official statistics. So SmartSets is a product developed by Telefonica, and what it does is, based on the levels of activity of the cell towers in different regions, which they actually, instead of doing a Voronoi tessellation, they just do a grid, they infer the amount of people in each of these cells, hourly, daily, weekly, and monthly. And then through a collaboration with a market research company that has demographic information, not only you have an estimation of the amount of people, but you also have an estimation of the gender distribution of these people and the age distribution of these people, and also what percentage of these people live there versus work there versus they're just passing by. There is other information, but we didn't use the additional information that SmartSets can provide. So as I mentioned, in this particular project, we had the estimation of how many people are in each of the cells, and then how many of these people are at home, at work, or passing by, then gender and age information. The London Borough Profiles data set is more of a traditional kind of like census data set. It has 68 variables they divide the metropolitan area in what is called LSOA, which are the geographic regions in the socioeconomic level, so the smallest sort of like geographic area that they cover, and which usually is about 1,500 people living in each of these areas. And then there is 68 variables related to the income, the unemployment rate, the ethnic distribution, etc. of all these variables. Of course, this data is not computed, it's computed every few years. It's not computed, obviously, daily or monthly. And then we had crime data that was coming from the Open Data Institute. And there what we had was, with a temporal granularity of a month, the number of crimes and the location of those crimes in the London metropolitan area. Because we wanted to find hotspots, what we did was we found that the median value was 5, and then we just classified all the regions into low crime or no crime, less than 5 crimes a month, and high crime or hotspots more than 5 crimes a month, more or equal than 5 crimes a month. From the Smart Steps data, we computed about 6,000 first-order features, second-order features, lots of different temporal windows, every possible feature that we could think of. And then we applied, again, feature selection, and we actually ended up with 68 features, which was the same dimensionality as the London Borough data set. So we wanted to see if with the same representation and the same dimensionality, how well the census data would do versus the human dynamics data versus the combination of both. So for classification, we also use random forests, and usually you use some kind of cross-validation approach for tuning the parameters and setting the parameters of the classifiers. And in this case, in the same as the socioeconomic levels, random forests outperform other standard classifiers. So we compared, well, we had a baseline, which was the one on the top, which was just a majority classifier, very poor performance. And then we compared a classifier built only using the London Borough data, then one only using the Smart Steps data, and then one using both. And then the Smart Steps data was actually outperforming the one built using the census data, and then when combining both of them, we could increase the classification performance to almost 70%. You won't be able to see much, but this is a visualization of the ground truth versus the classifier output. It looks roughly similar. It's very difficult to tell. At least the big hotspots, seem to be like identified, correctly. As I mentioned in the other project, one of the interesting aspects for us is not just the quantitative performance, but also the qualitative insights that we can get from building these models, because we can look at which features are the most discriminatory ones. So in the case of this project, one of the interesting aspects was that features that were capturing daily dynamics were much more important than features capturing monthly dynamics, for example, or weekly dynamics. Actually, a big percentage of the most relevant variables were related to the amount of people for whom that specific location was their home. And in fact, the regions that had an increased ratio of residents, so the regions that were not visited a lot by people, happened to be positively correlated with crime, which seems to support Jane Jacobs' theory of the eyes on the street, the theory of saying if a region has a lot of influx and a lot of people coming by, it's safer. Moreover, we also found that entropy-based features were very important. So entropy features had also been found to be important in other projects related to human behavior modeling using large-scale data. And for this project, we also found that they were important. So again, we found correlation between places having high entropy in the distribution between people being at home and at work, and also between gender and age, and the safety of the place, which also corroborates Jane Jacobs' theory. Something that I think would be interesting to you is that in the joint model, only 6 out of the 68 features were London Borough Profiles features, so were census features, and none of those features were in the top 20. So when the system could choose which features to use, it picked and it found that they were more discriminatory, the human dynamics features, than the London Borough features. This project is really just preliminary work. There are some limitations. One big limitation is that there were only 2 months of crime data, so 1 month for training and 1 month for testing. So there isn't really a lot of generalization that we can make here. It's just a starting point, and now we are trying to see if we can replicate these results and validate them with more data and in different metropolitan areas. As I mentioned before, these are some relevant publications that describe most of the projects that I have explained here. And now in the next 2 minutes, I'll just highlight both some opportunities that I see on using large-scale mobile data for official statistics and also challenges, because there are many challenges. So one clear advantage that I see, and I think it was illustrated through the projects, is the cost and the effort. This data is passively collected. This data is already being collected for other purposes. So the cost and the effort of using this data is significantly lower than having to create the data yourself by manual means. As I mentioned also, and this is very obvious, for example, in the crime project, the temporal granularity of this data is significantly higher than the temporal granularity of official statistics, because you can have access to this data on a daily basis, and it's very difficult to have access to create a census every day or even every month or every year. And this is a very controversial topic, and I put it there on purpose. You could argue that some of this data could actually be more accurate because there is no human in the loop, and maybe we humans introduce unintended biases when we are creating some of the data. And then in terms of the challenges, and some of the challenges have become very obvious recently because of the latest Ebola outbreak and some attempts of using mobile data for containing or understanding the spread of Ebola. So there are many regulatory and social challenges. Legislation and regulation is not updated to reflect the use of this data for these purposes. As I said, this data is being collected for other purposes. So we really need to update the regulation to contemplate this. In addition, and this is very important, there could be social consequences because of the temporal dynamics of this data and the fact that you can have access to this data every day and analyze it, in areas where there is civil wars or where there is social unrest or there are certain ethnic groups that are being discriminated, if very well-intentioned studies about migrations for other purposes are publicly disclosed and they could be used by certain governments or ethnic groups to target specific ethnic groups. So there might be unintended consequences of making a lot of not just even the data, obviously, but even the insights of the data available. There are many technical challenges, and this is obviously very exciting for us. Of course, and this is very important for official statistics, there is the question of the representativeness of the data and how well it can generalize. As I mentioned, almost everyone in the world has a mobile phone, but there are many people that don't have a mobile phone still. And also, even if they have a mobile phone, their levels of activity are not high enough. So even though it is definitely, I would say, the most universal sensor of human behavior, much more representative than, say, using social media, still there is a certain bias in the data. Another very big challenge is the lack of ground truth. How do you know that whatever you are inferring is real? Because if you are training your models with data from 5 years ago, reality has probably changed in the last 5 years. So maybe if your model is making mistakes, is the model really making mistakes, or is the fact that reality has changed in these 5 years? So the only way to really validate a lot of this is being able to do interventions, being able to make decisions, take actions, and then compare, regions where you don't use this information, regions where you use this information, and compare the results. And this also is fundamental to understand that all we can do is really identify correlations, not causality. So if we really want to understand any causal effects, we also have to do interventions. And then finally, obviously, there is privacy and security issues. Even if this data is fully aggregated, not all the data, but a lot of the data, is obviously personal data, and again, there has to be not only clear code of conduct and clear mechanisms to ensure privacy and security, but also updated legislation for that. So with all of this, I will just finish. My main point for you is to sort of like offer you this opportunity of looking into large-scale mobile data as a tool to be used for official statistics. And I think the question that I pose to you is, how can we all make sure that we can responsibly, take advantage of this opportunity? Thank you.